Artificial intelligence often feels like it exists purely in the realm of software, an entity detached from the physical world. We type a prompt and an answer appears, seemingly conjured from thin air. This perception, however, is misleading, which makes headlines about AI consuming vast amounts of energy and water all the more jarring. The truth is, AI is not some ethereal, immaterial intelligence. It is, in fact, industrial-scale computation. Every output we receive is the result of electricity being transformed into heat within physical hardware, housed in buildings that must continuously manage this heat. The controversy surrounding AI stems from its footprint, which has become significant enough to no longer be a mere rounding error within the broader economy. Moreover, the growth of AI is outpacing the infrastructure and policies that were designed to manage such advancements. The crux of AI's electricity consumption lies in the hardware that powers it. Modern AI systems are trained and operated using GPUs and specialized accelerators, each drawing hundreds of watts per chip. While this might seem manageable on a single machine, when scaled to thousands or even tens of thousands of chips running incessantly, it becomes a substantial and permanent load on electrical grids, reminiscent of industrial operations. Training large AI models makes this issue particularly visible, as it can require weeks or even months of continuous high-utilization computing. Computation demands do not scale linearly with model size. Instead, as models grow larger, the computing requirements often increase at a much greater rate. While the cost of training is significant, it is the ongoing demand for inference that remains a constant drain on resources. Even after a model is trained, serving millions of users involves triggering heavy real-time calculations. Popular AI systems cannot afford to sleep. They must remain available around the clock, across various global time zones, ready to handle bursts of demand that push them toward a state of perpetual readiness. A deeper structural issue contributing to AI's electricity consumption is rooted in modern computing architectures, which tend to waste energy by moving data inefficiently. There is a separation between memory and computation, leading to enormous energy expenditure as values shuttle back and forth between storage and processing, rather than being used for arithmetic operations. Nearly all the electricity used in this process eventually dissipates as heat, which presents a secondary problem, the need to expend additional energy to remove this heat. As for water usage, AI does not drink water, but data centers use it extensively for cooling purposes. Cooling high-density computing environments is unavoidable, and water is one of the most efficient and scalable coolants available. GPUs generate significantly more heat per rack than traditional servers, often by an order of magnitude or more, resulting in sharply increased cooling requirements as AI deployment scales up. Many data centers rely on evaporative cooling, cooling towers, or water-based systems to dissipate heat from hot components. When scaled to accommodate millions or billions of daily interactions, the resultant water consumption can become substantial. The controversy over water usage is heightened when data centers are located in regions already experiencing water scarcity, or when they compete with municipal or agricultural needs for water resources. Headlines sometimes sensationalize this issue by presenting simplified per-query water usage figures as if they were uniform constants. In reality, these figures can vary widely depending on data center design, local climate, and cooling methods. Not all facilities even use potable fresh water. Yet the core claim remains valid. AI's growth is driving up electricity demand, and the cooling required for this electricity use can lead to considerable water footprints. A key dynamic underlying many sustainability debates is the concept of efficiency gains, not automatically leading to reduced total consumption. As systems become cheaper per operation, their usage tends to increase, a phenomenon known as the Jevons paradox. This means that improvements in efficiency can paradoxically result in higher overall usage. A natural question arises: why not simply use the sea as a near-infinite heat sink? While seawater cooling is viable in limited cases and some industrial systems already employ ocean water through heat exchangers, it is not widely adopted for AI data centers due to several constraints. The first constraint is geography. Many hyperscale data centers are built inland, optimized for power availability, network connectivity, and land costs. Relocating infrastructure to coastlines alters latency, shifts fiber optic requirements, and concentrates risk. The second constraint involves materials, as seawater is corrosive and can rapidly degrade pipes, pumps, and heat exchangers unless expensive alloys and rigorous maintenance regimes are employed. The third constraint is environmental regulation. Discharging warmed water back into the ocean can disrupt local ecosystems, leading to strict regulations on thermal discharge. Finally, seawater cooling does not eliminate operational complexity. It still requires cleaning, treatment, and backup systems. While it can alleviate freshwater stress in certain areas, it does not globally resolve the cooling dilemma. Another proposed solution is liquid nitrogen, which at first glance seems like an attractive option due to its extremely cold properties. However, the physics of liquid nitrogen actually reverses this intuition. It is not a cheap cooling resource. Producing it is energy-intensive, involving the compression, cooling, and separation of air through industrial processes that consume large amounts of electricity. Often, more energy is expended in producing and handling the nitrogen than is saved by using it for cooling hardware. On a large scale, additional issues arise. Nitrogen boils rapidly at ambient temperatures, necessitating a continuous resupply. It poses safety risks due to oxygen displacement, and materials can become brittle under cryogenic conditions. The overall system becomes expensive, complex, and ill-suited to continuous industrial operation. While liquid nitrogen has value in niche scientific and engineering applications, it is not practical for cooling vast AI compute fleets. The idea of using space as a heat dump is another tempting notion. Space is cold, after all, so why not send heat into space? The misunderstanding here is that cooling is not solely about temperature. In a vacuum, heat cannot be removed through conduction or convection. It can only be removed through radiation, which is far less effective at the temperatures and surface areas practical on Earth. To radiate the heat produced by a large AI data center, an enormous radiator surface area would be required, potentially on the order of square kilometers, along with robust thermal coupling and structural support. Placing data centers in orbit exacerbates the problem. The cost of launching hardware into space is astronomical, repairs are difficult, radiation damages electronics, and power supply becomes a constraint. While space cooling is relevant for satellites which have no alternative, their heat loads are minuscule compared to terrestrial AI computing demands. The most radical alternative explored is wetware computing, which involves using biological elements like brain cells. The human brain, for example, operates on roughly 20 watts, while exhibiting capabilities that challenge even the largest AI systems. It functions using biochemical energy, glucose and oxygen, through electrochemical gradients, with memory and computation seamlessly integrated. From a purely energy efficiency standpoint, biology seems unbeatable. This has spurred real research into biological computing, neuron cultures, brain organoids, and hybrid neuron-silicon interfaces. In controlled environments, neuron cultures can be stimulated and measured, and simple adaptive behaviors can be induced. The concept is not science fiction, but the obstacles are fundamental. Neurons are not logic gates. They are noisy, adaptive, and non-deterministic. You cannot precisely address and set states as you can with transistors. Two ostensibly identical cultures will behave differently and drift over time. Training methods like backpropagation and gradient descent do not translate neatly to living tissue. The biggest bottleneck is input-output. Reading from neurons requires electrodes or imaging, while writing requires electrical, chemical, or optical stimulation. These interfaces are costly, slow, and challenging to scale. The notion that sugar is cheaper than electricity also falters when life support requirements are factored in. Living computation demands sterility, temperature control, oxygenation, pH regulation, nutrient delivery, and waste removal. Maintaining these at scale is akin to operating pharmaceutical-grade bioreactors. While neurons may be efficient, the system as a whole is fragile and operationally expensive. Biological computation could become useful in specific niches, particularly hybrid systems or ultra-low-power adaptive sensing, but it is not a realistic replacement for cloud-scale AI or services requiring deterministic functionality. Quantum computing is another popular future fix often cited for addressing AI's energy concerns. In reality, it is misaligned with the core workload and imposes extreme operational requirements. Many quantum platforms require millikelvin temperatures and dilution refrigeration, conditions that consume significant energy, often orders of magnitude more than the energy used by the quantum chip itself. Moreover, quantum computers are not general-purpose accelerators for all tasks. They excel in specific areas like factoring, quantum simulations, and particular optimization or sampling tasks. Contemporary AI workloads primarily involve dense linear algebra and deterministic numerical computation, which do not map well onto today's quantum hardware. The practical barrier of error correction is enormous. A reliable logical qubit may require thousands of physical qubits, plus continuous error correction overhead and extensive classical control electronics. The gap between current quantum machines and what is needed for large-scale AI is not a small engineering leap, but a very large structural gap. Therefore, quantum computing is better viewed as a scientific instrument for specific domains rather than a path to replace GPUs for mainstream AI training and inference. One alternative that truly offers promise is photonic or light-based computing. Photonics in AI computing is both real and promising, though it is crucial to frame it correctly. Photonic chips do not eliminate the need for electricity. They replace certain operations with optical physics, while still relying on electronics for control, memory, and general logic. AI workloads are heavily dominated by matrix multiplication, and photonics can perform forms of multiplication and addition through interference and phase shifts in waveguides and optical circuits. This offers massive parallelism with low resistive loss and reduced heat generation for the mathematical operations themselves. Photonic accelerators can deliver significant improvements in throughput per watt for specific operations. However, photonic computing is typically analog, which introduces noise and precision challenges. It struggles with state storage and conditional logic. It also faces conversion overhead. Data must be encoded into light and then converted back to electrical signals, with these conversions costing energy and adding complexity. For these reasons, photonics is more suitable for inference than for training, and it is best deployed as a coprocessor or accelerator rather than as a wholesale replacement for electronic computing. It represents a major efficiency improvement in the right context, not a silver bullet that will eliminate the need for data centers. The rebound effect still applies. As inference becomes cheaper, overall usage tends to rise. Moving beyond cooling tricks and exotic computing paradigms, the most plausible systemic solution lies in architectural innovation rather than magical thinking. Decentralized local AI is akin to volunteer or grid computing from previous decades, where idle compute was shared globally. However, today's hardware is exponentially more capable and includes dedicated AI accelerators in consumer devices. The sustainability advantage of this approach is considerable. Local devices are already powered on, already cooled, and geographically distributed. Using idle capacity avoids the concentration of heat that demands water-intensive cooling. It reduces the need to transfer data across networks, keeping sensitive data on device, which enhances privacy while lowering bandwidth and energy costs. This approach previously faced challenges due to heterogeneity, coordination overhead, unpredictability, and a lack of incentives. Devices varied widely in architecture and availability, and many distributed tasks required tight synchronization. Participants also bore the electricity costs with little benefit, leading to a weak economic model. The landscape has shifted. Many AI tasks, particularly inference, are now loosely coupled and parallel. Federated learning enables local training with centralized aggregation without the need to upload raw data. Incentive systems can be created through credits, reduced subscription costs, priority access, or reciprocal compute markets. While decentralization does not entirely replace centralized frontier models, it reduces their necessity by making most routine intelligence local. There is also a political economy dimension. Centralized AI centralizes data, control, and profit, whereas decentralized AI distributes capability and weakens the grip of proprietary systems. The resistance to decentralization is not always technical. In the near future, we should anticipate optimization rather than revolution. Smaller, task-specific models will become the norm. Hybrid architectures will dominate, with local AI managing routine tasks and centralized AI being called upon only when necessary. Cooling improvements will continue, including more liquid cooling and better closed-loop systems, and waste heat reuse will expand where infrastructure allows. Photonic accelerators will enter production for niche inference-heavy applications. Regulation and transparency demands will increase, pushing for clearer accounting of energy and water footprints. Equally important is what we should not expect soon. GPUs will not be replaced outright. Quantum computing will not become a general AI engine. Biological computing will not scale into industrial AI infrastructure. Data centers will not disappear. In the medium term, we can expect a more visible architectural shift. Decentralized and local AI will become economically attractive as centralized compute costs rise and privacy regulations push for data locality. Neuromorphic hardware, brain-inspired but not biological, will appear in real products for low-power, event-driven tasks, such as always-on sensing and robotics. AI usage will likely become tiered, resembling an energy market. Local cheap intelligence for everyday tasks, regional shared intelligence for heavier workloads, and expensive centralized frontier models for rare, high-value applications. Regulatory frameworks will mature from vague principles into concrete reporting requirements and incentives that reward efficiency and penalize waste. In the long term, AI will normalize into infrastructure. Intelligence will be embedded, contextual, and mostly invisible. Frontier models will exist, but will be treated as strategic resources for science, engineering, medicine, and national-scale modeling, rather than as default engines for trivial, everyday usage. Society will increasingly accept the physical reality that intelligence has a cost, and the assumption that bigger is always better will weaken under energy and environmental constraints. Across every step of this path, whether it be electricity, water, seawater cooling, liquid nitrogen, space, brain cells, quantum computing, or photonics, a single pattern emerges. Centralized approaches are bound to collide with physical limits. Exotic alternatives either fail thermodynamically, economically, or operationally at scale. The only direction that consistently reduces systemic pressure is distributing intelligence across many smaller nodes and reserving centralized compute for tasks that truly require it. The AI energy debate is not fundamentally about whether we can invent a clever coolant or a magical chip. It is about whether we will continue to build intelligence as an always-on centralized utility or redesign it as a distributed capability that respects physical reality. The future will not be determined by one breakthrough. It will be shaped by constraints forcing architecture to evolve, and by whether society is willing to accept limits instead of assuming intelligence can grow without cost.